This video is on inverse functions. So the inverse of a function is another function that undoes the original function. And the notation that we use for this is, well, it looks like f to the negative 1, but this isn't an exponent. We read this as f inverse. And I do want to be very clear that that is not an exponent, it only looks like one. It has a different meaning, it means inverse function. So let's look at an example with some tables. So if I have a function that when you put in 6, you get out 7, then the inverse of that would be when you put in 7, you get out 6. So if you do one and then the other, you get back to the number that you started from. And you can do that in the other order. If you use the inverse function first and put in 7, you'd get out 6, and then do the original function, put in 6, get out 7, and you're back to where you started from. And notice that these tables are almost identical. All I had to do was swap the x and the y column. So let's actually have those things written out for us. The functions are essentially the same with the x and the y swapped. And remember, this is the symbol for function composition, where we use one function as the input for another function. So if we apply one function and then the other in whichever order, we always get back whatever our original input was. So if we start with 13 and then do f of 13, we get 3. If we do f inverse of 3, we get 13. Next, let's look at an example. I want to know if the functions f of x equals 2x plus 7 and g of x equals 1/2 x minus 7 are inverses. It certainly seems reasonable. In one case we're multiplying by 2, in the other case we're multiplying by 1/2. We're adding 7 here, subtracting 7 there. It seems reasonable that they might undo each other, but in order for it to be true, we need to be able to compose the two functions and get x back. So we're going to start with f compose g of x. Remember, that is f of g of x. So what I've done is used g of x as the input for f of x here. Now I can just use algebra to simplify and distribute that 2. Now, since there's not any multiplication or anything happening to those parentheses, I can just drop them and combine like terms. And I get x minus 7. So when I compose the two functions, I do not get x back. These are not inverses. So let's look at another example. Our f of x equals 2x plus 7 and g of x equals x minus 7 all over 2 inverses. So again, we're going to compose the two functions and find f of g of x. This time when I do that, I multiply 2 times my fraction. This 2 will cancel with the denominator and give me just x minus 7. Plus the 7 on the outside. When I combine like terms, I just get x. Now, it's not enough just to do it in one direction. You do need to check both directions to see if the composition works in both ways. So let's check g compose f and make sure that it is also just x. So g is my outer function this time, and I'm using f as the input of g. So I get 2x plus 7 minus 7 all over 2. When I when I combine my like terms on top, I get 2x over 2. And then the 2's cancel, leaving me just with x. So yes, these are inverses, since f compose g of x is x, and g compose f of x is also x. F and g are inverses. So we can check to see if things are inverses by composing them and seeing. If we need to find inverses, we need to remember that fact about inverse functions essentially just have their x's and y's swapped. So if I want to find the inverse of y equals x over x minus 2, I start by writing down the same function except swapping the x's and y's. Notice where there was a y, I wrote an x. Everywhere there was an x, I've written a y. So I can multiply both sides of this by y minus 2. That'll clear the denominator on this side and give me x times y minus 2 on that side. I can distribute that x. Now, the point of this is to get this to write y as a function of x. So I need to get all my y's together. So I'm going to add 2x to both sides. That'll move it over here. I'll subtract this y from both sides, and it'll end up over here, leaving me with xy minus y equals 2x. Then I can factor out a y. This is important because if I'm going to write this as y equals something, I need to only have one y. Now that I have this written as y times x minus 1, I can divide both sides by x minus 1, and now I've got y equals 2x over x minus 1. So this is the inverse of y equals x over x minus 2. So if my original function is x over x minus 2, then f inverse of x is 2x over x minus 1. So now let's talk about domains and ranges of functions and their inverses. Remember, we are swapping x's and y's. So the domain of a function, the set of all the x's, is the same as the range of its inverse, because that's the set of all the y's of the inverse. The domain and the range get swapped when you swap the x's and y's. Similarly, the range of a function is the same as the domain of its inverse. So this is actually very useful when we're looking for the ranges of things. We know how to easily find the domain of a function like this. It's going to be the set of all numbers so that the denominator is not 0. The only value that makes this denominator 0 would be 2. So now I have a table to fill out. So the domain is everything that's not 2, which is, in interval notation, is negative infinity to 2 union 2 to infinity. And the domain of a function is the same as the range of the inverse function. So those two are the same. Now, in order to answer the range of the original function, the easiest way is to look at the domain of the inverse function. So notice that I used the same function from the previous slide, where we had found that its inverse was 2x over x minus 1. By looking at this, we can tell that the only number that would make the denominator 0 is 1. So the domain of the inverse function, it would have made more sense to fill this in first, but the domain of the inverse function is negative infinity to 1 union 1 to infinity. And that is also the range of the original function. Finally, let's talk about invertible functions. Not every function has an inverse. Since we are swapping x's and y's, you might have a function that when you try to swap the x's and y's, you end up with something that isn't a function. Functions are only invertible if they are one-to-one. That's the only way that you can swap the x's and y's and end up with something that is still a function. So let's look at some graphs, some examples here. So this is our old friend, the squaring function, y equals x squared. This is not one-to-one. It's not invertible. If I tried to swap the x's and y's, notice how the y value of 1 has two x values associated with it, 1 and -1. The y value of 4 has two x values, 2 and -2, associated with it. So if I swapped them, I would have an x value with two y values associated with it, and that wouldn't be a function. But I can restrict the domain. I can look at this parabola and say, okay, well, I'm only going to take, half of the parabola, everything to the right of the vertex. Now I have something that is one-to-one, and when I'm only considering this restricted domain, like I said, it's not invertible on the full domain, but it is invertible on the restricted domain because it is one-to-one on that restricted domain. And the inverse of the squaring function on its restricted domain is our old friend, the square root function. So that concludes our lesson on inverse functions.